Hi all, today we are going to see single phase electrodynamometer. The construction of a single phase electrodynamometer is shown in the figure. It consists of fixed coil which act as the current coil. This coil is split up into two parts and carries the current of the circuit under test. Therefore, the magnetic field produced by this coil is proportional to the main current. So the two identical pressure coils A and B are pivoted. A and B are pivoted on a spindle constitute the moving system. Pressure coil A has a non-inductive resistance are connected to in series with it. So resistance A are connected to it series. So and coil V has a highly inductive choke coil L connected in series with it. The two coils are connected across the voltage of the circuit. The values of R and L are so adjusted that the two coils carry the same value of current at normal frequency. That means R equal to omega L. The current through a coil A is in phase with the circuit voltage, while that through coil B lags the voltage by an angle delta, which is nearly equal to 90 degree. The angle between the planes of a coil is also made equal to delta. There is no controlling device. Connections to moving coils are made through the thin silver or gold ligaments, which are extremely flexible and thus give a minimum control effect on the moving system. This is the construction of this single phase electrodynamometer type power factor instrument. The working principle of the single phase electrodynamometer type power factor measurement instrument. In order to simplify the problems, we assume that the current through coil B lags the voltage by exactly 90 degree. Also, that the angle between planes of a coil is exactly 90 degree. That means delta equal to 90 degree. Now there will be two deflecting torques, one acting on coil A and the other one acting in coil B. The coil windings are so arranged that the torques due to the two coils are opposite in direction. Therefore, the pointer will take up a position where these two torques are equal. Let us consider the case of lagging power factor of cos pi. Now we will see the mathematical expression for the deflecting torque for a coil 1, that means coil A. T1 is equal to kVIm. So T1 equal to kVIm cos A sin B, where M is the maximum value of the mutual inductance between the two coils A and B. B is the angular deflection of the plane of reference. Now the mathematical expression for the deflecting torque for coil 2, that means coil B. T2 equal to kVIm cos 90 minus A sin 90 plus B. That means is equal to kVIm sin A cos B. At equilibrium, we have both the torque as well as equal. Thus on the equating T1 is equal to T2 and we have A is equal to B. So T1 is equal to T2. Now at equilibrium condition, because same values only there, T1 and T2. Okay. Next at equilibrium we have both the torque as equal, thus the equating T1 equal to T2 and we have A equal to B. From here we can see that the deflecting angle is the measure of phase angle of the given circuit. The phasor diagram is also shown in the circuit such that the current coil 1 is approximately at an angle of 90 degree. So this is the current coil at 90 degree and voltage coil, this is to current coil 2. So this is the IB, this is the I, this is the IA, current in coil 1, this is current coil in B coil, current in B coil, this is current in A coil, this is current, this is voltage. The voltage and current is 90 degree. The angle between voltage and current is A. So now we will see the advantages of electrodynamic type power factor meter. Some of the advantages are the losses are less because of minimum use of ion parts and also give less error over a small range of frequency as compared to MI type instruments. That means moving ion type. And high torque is to weight ratio. Okay. So next are disadvantages of electrodynamic type power factor meter. The working forces are small as compared to moving ion type instruments. The scale is not extended over 360 degree. The calibration of electrodynamometer type instruments are highly affected by the changing the supply voltage frequency. Next, they are quite costly as compared to the other instrument. Next, we will see the comparison with the moving ion power factor meter. So now we will compare this electrodynamometer type power factor meter with moving ion power factor meter. In electrodynamometer power factor meter, working forces are very small as compared to the MI type moving ion type. The scale of moving ion type extends over 360 degree. The electrodynamometer type is more accurate than the moving ion type. Okay. Next we will see the construction of three-phase power factor meter, that means three-phase electrodynamometer. It consists of two fixed coils FF connected in series, one of the phases and carries the lines current as shown in the figure. Next, the two identical moving coils A and B are fixed with their planes 120 degree apart and are connected across the two remaining phases respectively through high resistance as shown in the circuit diagram figure. In this case, there is no necessity for phase splitting by artificial means, since the required phase displacement between the currents in the moving coils can be obtained from the supply itself. So next we will see the three-phase power factor meter working principle. When the three-phase power factor meter is connected in the circuit under balanced conditions, the angle through which the pointer is deflected from the unity power factor position is equal to the phase angle of the circuit, because the two moving coils are fixed 120 degree apart. The deflections in three-phase power factor meters are independent of frequency and waveform, since the current in the two moving coils are affected in the same way by any change of frequency. So this is the construction and working principle of single phase and three phase electrodynamometer type electrodynamometer type power factor meters.